on the infrared survey. Now, the reason I'm showing these are the three giant galaxies in our group called the neighborhood. Okay. This is our neighborhood. Andromeda and the Milky Way, they are approaching each other. Okay, there is a measurable speed now, proper motion measurements, so we know when this will collide. And the distance between this to the Milky Way, do you know what it is? You know, what's the distance between this? Say 2.5 million light years. Can someone convert this to parsec? Do you know? Do you know? Huh? You say light year. So, 1 light year, how many parsecs? So 2.1 million. You do it at the end of the class. You tell me. This is not exactly what I wanted to get in, but it's important to get to know the numbers. And so these three are basically the dominate the local group. Okay? These are the local group of our galaxy, and you might have heard that the galaxies live in groups. And groups is basically a few galaxies together. And then on an even larger scale, galaxies live in a cluster of galaxies when there are a few hundred to few thousand galaxies are clustered together. So just to get familiarized, you see what we try to understand is very slowly that how these galaxies are and what their shape and what their morphology, and the idea of the dynamics of the galactic dynamics is to understand how do these structures form, why do they have this kind of shapes. Yeah. That's the idea of the dynamics. Now the word itself says that the dynamics is basically something to do with to understand the motion of stars in the galaxy. Galaxies are made up of stars. Anyone disagree? No. Do you know how many stars in a galaxy? 10 to the 11. Everyone? 10 to the 11. Right? But there is a range basically which is, let's say, about a billion to all the way up to 100 billion stars in the galaxy, like for example in Milky Way, and they must be moving around each other, like the planet moves around the sun. Very similar fashion, but slightly complex, and the complexity of course increases as you get to know much more. So the motion of the stars are supposed to give you an insight into how this shape came to be. That's what we need. Now we will progress towards that, see how much we understand and what we know. So if you look at the shapes of these galaxies, they are all look very different. And if you look into the various local galaxies, these are not exactly these are not the galaxies from our local group. But if you look at the 20 megaparsec distance from the Sun and go around, and you see many such galaxies here. And you see some galaxies have a very elongated structure in the center and have a spiral arm. Do you know what this is called? Bar and this spiral arm. So this galaxy is the barred spiral galaxy. This galaxy also has spiral arm, but there is no elongated structure. It's not barred spiral, so it's just a spiral galaxy, right? These galaxies look very, very different from this. So now you can see that a galaxy is a three-dimensional object, right? So, and it can be oriented at any angle. If it's whatever the Euler's angle, So it can be at any angle in the space. And what we see is basically the projection onto your camera. This is what the image on the camera. Now this is supposed to be an age-on galaxy. So if you look at like an age-on galaxy, you see this. Maybe like the face-on, it's like you see the face-on galaxy. It's more like a face-on galaxy. This is age-on galaxy. So when you look at an age-on galaxy, two age-on galaxy, they are very different, right? So which means that this galaxy intrinsically is different than this one. That we understand. How different they are? You see that something is like a box shape here. There is no box shape here. Okay. The shape, what we see here, is basically coming from the distribution of light. And the lights are emitted by the stars. That's very simple. Okay. But it's not simple in that sense that okay, if the stars are emitting light, so we should be able to know how the light is distributed. But it's not like that. These stars are moving different. Okay, that's where the complication starts here. And you can see that maybe this galaxy don't have this structure at all, the center. So there are many ways to understand this, but we'll see how. Okay. This is again coming back to the Milky Way galaxy. This is again this is a fake image. It's not real, but every bits of pieces of this information that you see, they are real. Which means it's a basically artistic situation. It's a reconstructed image inside. Okay, so this Milky Way has a bar and it has spiral arm, and we are right here in terms of astronomical distance. Is from the center of the galaxy, our galaxy, to the sun is 8.5 kiloparsec. Okay, 8.5 kiloparsec, and sun goes around the galaxy. Sun goes around the galaxy with a speed which is roughly about 220 kilometers per second. Do you know what is the speed of Earth around the sun? Anyone? 30 kilometers per second. So we go around the sun 30 kilometers per second, and the sun goes around this and 220 kilometers per second. Right? So, and then these are the spiral arms, and then the way to understand the spiral arm in the galaxy, that you can think about a very suppose let's say this is a center, this is just a schematic of a spiral arm, right? What you see in the spiral arm is basically a much more light, right? Much more light than here. So which means that between the two spiral arms there are a bit less dark places, right? The contrast is less, but actually it is less light there. Which means that if I look at the between two arms here, there are less dense region. This is high dense region in terms of the stars, number density of the stars. Now, which means also that the spiral arms where you see here, okay, so this has more number of stars, so which means how do I say that this is over dense, so the potential is deeper? Huh?
Higher mass.
Higher mass, and how does it translate to potential?
GMM by repeating the
Not that. You should be with more. It should be coming from what's the equation? You have a density and directly connects to the potential. The density directly connects to the potential. So you see the potential, so a star which is go around this, you suddenly feel the potential where is deep. Okay, and then it have a bumpy like this, it go around, bumpy like this, and then it go around like that, right? So it suddenly feels the potential very deep and then comes out and then so that's how. So the motion of the sun is actually quite bumpy in the Milky Way. Must appreciate how difficult must it be. This is a different story. But for dynamics, unless you follow this, so you will not appreciate. But this is where the spiral arm at least causes what the motion of this sun around the galaxy. It is not like the planet motion which goes around the sun in an elliptical orbit. Smooth mostly, apart from the asteroid hazards and stuff like that. No issue. But this is a really bumpy motion. Now, already we come to this that if we have a density, then we can think about the potential. If we have a density, we can estimate the potential, right? Now, how do we first get the density of a galaxy, right? That's where the first thing. So we must know how to measure the density. Have you learned a bit on this in past classes? Hmm? So this is a simple slide to explain you that what we measure and what we get from it. Okay? What you see is what we measure from an object. Like imagine this is an object in the sky. Okay, and is at a distance d where your telescope is and where your detector is. Okay, you take a camera and you take an image of this. Right? Now, what we measure from any of these small annuli, suppose I can think about this as a small annuli. So this is a very messy. So you can think about it in R, so R plus dr, right? This is R, and then this is R plus dr, delta R. And from here, this will subtend a solid angle at the detector, right? Which is a distance d. What we find here is that suppose this is a luminosity L, then the flux would be 4 pi d square. L divided by 4 pi d square. That's the flux. The surface brightness that we measured here is a flux divided by the solid angle, which is basically the area subtended at the detector. So it's a theta is in a small angle approximation is basically delta R by d. So on the top you have L by 4 pi d square, in denominator you have delta divided by the d square. So which means that what we measure on the detector is a surface brightness which is independent of the distance d at the approximation of very low redshift. If it is a very far away object, then the curvature will becomes important and the light bending and all that stuff. So then this formula is not exact. Then there will be dependence on that in terms of a redshift, which is basically 1 divided by 1 plus z to the power 4. Z is the redshift of the galaxy. So that's a different story, but as long as we are in the local universe, okay, in the local universe, this works pretty well. The surface brightness, what we measure by the detector, becomes an independent of the distance. You don't need to know what distance the galaxy is, right? Now, once you measure the surface brightness, okay, so actually what you see on the detector is probably you have a rectangular or square array of pixels, right? In each pixel, you have some kind of a distribution, and so from I, comma j equals to 1 to let's say n, then to let's say m, okay, or you can say it's n by n. In an array, you basically measure this surface brightness distribution. Okay, you measure the surface brightness distribution. So every pixel you can count, and you can say that collectively total surface brightness. So in principle, you could just say that I do basically I, ij, R equals to 1 to n, J not equals to. Right? Very simple. So it gives you the total I naught. Total surface brightness is just sum over all the pixels. Simple. So that's the image. Once you do the I total here, the total light that is collected by here, okay, then you can actually estimate what is called the magnitude of a galaxy. So which is basically apparent magnitude, which is minus 2.5 log 10 base I total plus some 0 point. Okay, this is what we can measure the apparent magnitude. Typically apparent magnitude. The larger this number, fainter the galaxy. Right? Larger the number, fainter the galaxy. Okay. Now, what you see here, what I make suffix here is the m lambda. Right? This is also a c lambda. C lambda is kind of a 0 point. It's like when you take an observation with a telescope, you measure light, but you have no idea how to quantify, how to measure. You need a reference. So that's why you look at the point the telescope to a standard star, the same condition, and say, okay, this is the flux given this. So you get a reference. So you measure so 0 point is measured with respect to some standard star. So it's like you have a reference. With a reference, you measure the flux. Otherwise, we don't have an idea like how to you measure some photons, but how do I know is it like what is the it's not an absolute constant. Okay. Now you see this I put in a so this is also 0 point depends on like at what wavelength band you observe, right? And the magnitude, apparent magnitude that you measure, and also depends on the lambda of the pass band. Now, what are the different parts? So this should be also function of lambda, right? I total that I measure is also should be function of lambda. It's exactly true. So when you there are many the telescope has lot of filters, like often the filter has a many different kind of shape. So you can the response T versus lambda, like this is some kind of a band pass filter. So it's a very lambda 1 to lambda 2. So all the light that is collected within this will be coming to you. Else this was not there. So we measure light in a given pass band. Okay, for example, SDSS survey master card that it has 5 pass bands. So there are many actually like pass bands through which we measure the light. Okay. Now, so this is the apparent magnitude of the galaxy, and once we have the apparent magnitude, we can actually estimate the absolute magnitude of the galaxy if we know the distance. Right? So that's why, and then from the absolute magnitude, we can estimate the luminosity. So that part is fine. So this can be done at different pass bands. It can be in ultraviolet, it can be in optical, it can be in infrared, it can be in any other band. So you measure light in a given pass band from the galaxy, and that's the apparent magnitude belongs to that particular pass bands. Okay, so given a pass band, there can be also a mean wavelength, lambda mean or effective. Okay, so which is basically your T lambda, D lambda, integration, lambda 1 to lambda 2. This will be lambda. So you will call that the apparent magnitude at that effective rate. Right? So this is what the basic measurement is done, and that's how we estimate the I as a surface brightness of the galaxy at a particular wavelength. Okay. Once you see that, you will see that if you look at elliptical galaxy, for example, this is an elliptical galaxy example, and this I think you have learned that in the last class, right? This is called the Divabulus profile. Have you heard about that? No? Cersei? statistic profile? No. Right? You didn't go through this profile decomposition. Anyway, so I thought it is the answer. I was going to skip, but what happens is that here what I said is basically you see light in this in your camera pixel, right? And you sum up total and you get the basically total light from the galaxy. Provided there is nothing else. I'm talking about ideal conditions. In general, there can be very bright star here, which is contaminating light. There are many nitty-gritties and details here. I'm talking about the ideal condition in which there is nothing else, not even this background, okay, which will add to that. Because every time you observe a galaxy in the sky, there will be light from the galaxy and light from the background will come together, right? So the photons, number of photons that we see, it will be sum total of the photons from the galaxy and from the background, which is behind the galaxy. Okay. So we are not talking about those details here. I believe this will be taken care of. That is all. Now, so when you look at this, I said the total sum, but you can also do something called, for example, let's say I find the center, bright center here. I say that okay, this is the center of the galaxy. There are ways to find the center of the galaxy. Using, for example, you could take, if you have n number of particles, you can find the center of mass, right? So similar way, you can find the center of light. Like each pixel is a mass element and its position is x, I and y. So the x into light, I, okay? And that give you like basically if you have understood that is the center of light. So once you find the center, one can draw an ellipse. You can draw concentric ellipse. Okay? On the galaxy. Is it visible? You understood? So one can draw a concentric ellipse. Each of these ellipse can be fit to the light distribution of the galaxy. So this is done typically something called the IUCAA task. Okay, there is a standard task in the astronomy which is done the IUCAA task, ellipse fitting routine. But the philosophy is very simple. It's basically say that you take a small region in which you have n number of pixels here, and you say that I want to fit the n number of pixel distribution using an ellipse. Okay, so I have an equation for the ellipse. I have this open of this, and it's an xy distribution of the light here. So I can fit an ellipse here, two-dimensional ellipse. So that's the philosophy which is done by that. So at the end, you get the orientation of the ellipse and the total light within the ellipse. So then you can say, I plot this as a function of phi of r. R is the semi-major axis of the ellipse. So you get the semi-major axis here. Then another semi-major like that. And then you say, okay, I have some numbers. Okay. And then the ellipse will be also oriented. Every ellipse is oriented in one. Everything is oriented in one direction. Okay. Then you have also the position angle of the ellipse versus the radius will should be constant. Fine or no? Question asked because I am going to tell many things in a very short duration of time. So please ask. So then this is how the surface brightness profile looks. So instead of total surface brightness, I can do as a function of semi-major axis.
So this you were assuming that the center will be the brightest point because we found the center of light as the center of the galaxy.
Yes. In general, there is a slight complication with using that kind of terminology. Is that suppose I have a galaxy here, I have another situation. I have a galaxy here which is like very bright, but also there is something like even more brighter here. But then I will be like a little bit confused. The bright spot is not always the center of the galaxy. So if we think that this is not the center of the galaxy, we have to mask this spot. But this is where the human intervention comes in. One cannot like make you just give the machine. Maybe we'll say that, oh, this is a right center, so you'll define that. So you'll find the center here. But this actually is not the center. Okay.
Sir, so we approximate the center. How do we find what is the center of the galactic and where to start it?
So suppose this is a case, right? This is a case, and I think that to my general understanding of what the galaxy looks like, that this cannot be centered because this is also bright here, it's bright. So I think this is not the center. So what I do is basically I put a square box and I mask it. Okay, and I mask part here, so I left out with these pixels. So I take, for example, this center cannot be here, center cannot be here, center cannot be here. That's fine. So I said I draw a box here, not small enough, but not too large enough to take the full box size of the galaxy. Large enough, and in that I know how many pixels are there, I and j, and I can say that how do I say, like, let's say I into I, the mass of the pixel, then the light in the pixel, and the position on the pixel, right? Just sum it over divided by the within I. This is how basically the center CM will be found, right? So this is the mass of the pixel. Treat this as the mass of the pixel. This is the light of the pixel. So it's the center of light. Here, everyone. So this is how we find the center of the galaxy, and this is very important. Actually, if you want to do this task, if you do derivate the center, you find with erroneous results. Okay? Whatever. So then we have a data point here. A set of data points. Now you have tons of fitting routines actually. Okay, so this is a surface brightness versus semi-major axis SMA. What you do here is that often if this data point doesn't look like that, this is the point look like this. Okay, it's not like that. And often you don't see like, what do I fit with it? I don't have any clues, right? So I need a function. Like you need to build that intuition first. So if you measure the total light within an ellipse, then another ellipse, then another ellipse. That's how you want. So what you do is basically take a log of this, log of I, and fit as a function of same measure x. So if the I, if you some part of the find, like now following a straight line, then this part must be, I must be e to the power something, e to the power minus r, right? Because it's log of I, so it should be like, although it's a 10 base, but it doesn't change the log 10 be, right? So this would be straight line. So if you find a certain segment of your observation of surface brightness into a straight line, then that part must be exponentially function. Then there can be like no difference. So this is what basically I am trying to show you here. So you see this is where the I of R, and this is really is not very complicated actually. It is the exponential function. You look at this, then minus some number r to the power 1. Right? R to the power 1. This minus 1, well, plus 1, we should go in here. Is a constant. Is an exponential. It's essentially and e to the power I of r is basically e to the power minus r by re to the power 1. Essentially that is. Right? So it's basically exponential kind of distribution. Okay. You see the plots here. Now that's also very interesting here. You see, if you have done this is r divided by some arc second. Arc second is the angular scale of the sky, right? So this is the scale, the problem. You see, this is only the straight line. Why wouldn't it be straight line? Because it is r to the power 1/4. I consider that as some kind of a variable here. So let's say consider this as a z, so e to the power minus z. Log of I is plotted here. Log of I is plotted here. It's a surface brightness. It's basically a straight line. Okay. Or if you need surface brightness, mu b is a surface brightness, is a log. And then this is a log of r, we just falling with it. So idea is that you measure this as surface brightness profile as a function of strain measure axis. That's the data point. X versus y. X versus y, when you look at plot it, you can plot it in many different ways. You plot it as a I log of y versus simple r with it's like sum distribution. Put it as a log of r versus log of r. Like by plotting this, you would know whether one of these functions would be fitting very easily. That's right. So this is a famous profile called the Divakudas profile. In it, this kind of profile, e to the power minus r over re 1/4 fits almost all the galaxies, which are elliptical in nature. So most elliptical galaxy, bright, big elliptical galaxy, follow surface brightness profile. Go quick. I'm gonna very, very slow. Now here is a spiral galaxy. Again, the surface brightness is plotted on the y-axis versus the radius. Same measures. You see a large part of the is falling almost like a straight line into, which means the profile is exponential profile. Is clear? Exponential profile has two parameters. One is the central surface brightness and another is scale length. This is basically the slope related to the slope. Right? So you see, once you see this picture in a plot, you will immediately know this is an exponential galaxy or some surface brightness distribution which is governed by an exponential underlying distribution. That's all. So the light in a galaxy, in a spiral galaxy, mostly are exponential in nature. In a large part of these galaxies. If you say that how is the light distribution is in a spiral galaxy, it's an exponentially falling. In an elliptical galaxy, they are falling like e to the power minus r over re. Okay, e to the power minus r over re. So these are the two different kind of major segregation in the light distribution in galaxy, elliptical and spiral. If you go to the center of the galaxy here, you see center of the galaxy as we go from outer part, we fit ellipse here, concentric bit. You see center part, suddenly there is a lot, it's not fitting with the exponential distribution. So here is there must be something else, and this is called the bulge of the galaxy. This is a bulge of the galaxy. If there is a bar also, it also won't fit. It will also be like a deviating light. Okay, in many cases. So which means that when I look at the surface brightness distribution in a galaxy, okay, if I carefully examine, I can find out that intrinsically they are following different kind of light distribution. That's all we must learn from. Is there any question? No? Okay, great. Now we have to go back.
So I have a question. So in case of a spiral galaxy,
yes,
you have these more dense regions and less dense.
Yes.
More dense regions are brighter, less dense are different.
Right.
So why isn't it reflected in the explanation?
Good question. So have you understood the question? Everyone? We need to ask. Okay. So let's say this is where the again a galaxy y, x, and we say okay, from the center. This is what basically the spiral arms here, or there are many arms here, like very messy, right? And you fit ellipse, and this is over dense region, this is under dense region, this is over dense, under dense region, this is over dense region, like Now, what is done in this ideal ellipse task is it fits a two-dimensional ellipse. So it defines a region, it defines an R, it defines a region. So what it does is basically from the center it creates segments. This is basically what is in the code, okay, but you will understand. So I have, let's say, an ellipse divided by like n segments in different azimuth. Then I'll encounter this part, I'll encounter this part, I'll encounter almost wherever there is a spiral arm on. Is it clear? Where it is? Listen. Now, from each segment, I calculate the total light. Okay? And it's like if you open it, it will be like I of phi as a function of phi. Right? So it will be phi is azimuthal angle. What in ellipse does is basically the average out this part. They average out this part. That's why you don't see the variation. It's very as simple as that. But if you make your own code, then you don't need to do this. You can just fit in some way that you can recover this one. But that's the basic reason. If you use automatic code, this is what you will get averaged out, which is called the azimuthally averaged profile. That is one. But there is easier, it's not very difficult. So you can just calculate this and you say, okay, at a given phi, but then you won't be able to fit ellipses. Okay. So idea is to basically go along this line and see the azimuthal variation and see the arm. So this is how one can do like otherwise also there is a very other interesting way of doing things. For example, so which means that essentially what am I looking at is I as a function of x and y, right? Which I written Ij is basically function of x and y. Function of x and y in a polar coordinate it will be I as a function of r and phi. Correct? Easy transformation just from the pixel xy pixel to r phi coordinate. From the r phi coordinate, once you have r and phi, I can think about this as some I naught plus a1 e to the power I m phi. Right? M is equal to 1 to a1 m. Sorry, m. Fine. This is some amplitude. E to the power I m. So what I've done here is I've done a Fourier transform. I have any function which is r and phi. Right? Any function of r and phi, I can actually think about doing a Fourier transform. This time I have an image which is stored in this r phi polar coordinate. I can think about this as a Fourier transform. Once I do the Fourier transform, I can get I naught, which is the phi independent component. So which is average stuff. I should get this. Okay? And then this part is basically coming down to all those wiggles around. Spiral arm, maybe there is some asymmetry, any damn thing that you think about. Okay, so this is how it's basically all of the this is called the axis symmetry. Axis symmetry. This is all due to the non-axis symmetry. Axis symmetric component and the non-axis symmetric component. So what does non-axis symmetric component contains? It contains spiral arm, like anything that does not have axial symmetry. Or like in other words, this also can be think about as a non-axis symmetric term, but with m equals to 0. Right? So given a surface brightness distribution on the sky for a galaxy, I can think about this galaxy as a decomposition in terms of a an axis-symmetric smooth distribution. On top of that lies this kind of spiral arm. And other anything that you feel like is not symmetric. You feel sometimes if you look carefully, this side looks bit more elongated from the center, right? All this need not be just the problem with your eyes, maybe here. Okay, astronomers need to have a very good eye to pick small things here, and that's very important. It can be that this is an m equals to 1 component. Okay, and m equals to 1 component is nothing but m equals to 1 what is a cos phi term, right? In the real part. So it's basically have an ellipse, or you can think about a circle, and I think about a circle like this. It's shifted bit. So this part will be less dense, this is the over dense. Right? So is m equals to 1, then spiral arm becomes m equals to 2. Why? Because if you go around the galaxy, and I say it like this, I say, okay, I take a radius here, and I go. I see over density once, twice, so m equals to 2. I make another arm, I go around once, twice, thrice, so m equals to 3. Okay, so like that you can say m equals to 4 also. Okay, and one can go all the way up to many large numbers. So that kind of galaxy, when m is very large, is called the flocculent galaxy. Flocculent galaxy. Not very common. Most of the time in the sky you see arms with the 2 arms, 3 arms, like that, maximum with the 2 arms, right? Spiral arm. So it's a flocculent galaxy. So the main part is that I can think a galaxy like a spiral galaxy has a smooth distribution of light. On top of that, I can think about something that is like a spiral arm, like a bar, like an asymmetry, all kinds of non-axis symmetric features. Fine. Here I'm going to stop now with the. I hope you have got some idea about the surface brightness distribution in a galaxy, the light distribution in a galaxy. Any question in this? Yes. Correct. So when the galaxies are not face on, you have difficulty. You have obscure view. You cannot fit ellipse actually easily. So most often those galaxies are not analyzed, but they are not basically people don't take into consideration. They just ignore. It's a difficult task because I can give you a simple example. Imagine you have an edge on galaxy like this, right? This is the projected axis, right? Now say if you have to do ellipse fitting, right? So if you want to do ellipse fitting, you have to, because it depends on how the edge on is. Like say, I take a region here, take a region here, and then I say, okay, I have divided. You see, if you start doing this, it becomes very big. This angle, because it's a, imagine this is almost 2D. It's almost impossible to do, right? You can't fit ellipse in there. But there are other ways one can do. Okay, I say that, okay, I draw small boxes here. I take distribution of light from this, and I plot it as a I as a function of the projected x. But most of the time, the alien galaxies have difficulty because what you measure on that, depending on what you measure as the ellipticity of the galaxy. Okay, this can be a difficult task. For example, anytime you see an ellipse here, you can measure the same minor axis and the same major axis, which is like B and versus A, right? And we can define an ellipticity which is 10 times 1 minus B by A. Okay. When B equals to A, this is 0. So for a circle on the sky, you have ellipticity which is like for this, p is very small, so ellipticity very close to 1, right? So now in the Hubble classification scheme, we have a trouble here. Now a b by a equals to circle can be an elliptical galaxy also, in a face on completely, which is called an E0 galaxy. Each of these elliptical galaxy, I'm not going to show you the Hubble Tinico diagram where it shows that E0 to all the way up to E7. 0 means b by a equals to b by p equals to a, so it's like E0. Then E1, E2, E3, E4, E5, E6, like, and E7. Okay. So how you see the ellipticity is very simple measurement. You take a galaxy on the sky and measure the same minor axis on the outer part and say then define the ellipticity. Why I bring this to here? Because your question is that what to do with the elliptical galaxy, edge on galaxy. Edge on galaxy can have E6 also. But then is it an elliptical galaxy or is it an edge on this galaxy? That confusion will be. It's not very easy unless and until you go to dynamics. Do you understand? I can have a very elongated galaxy, which I showed in an image, but then also an elliptical galaxy can also be very elongated, which is E7 or something. Okay. Now, how do I know whether it's an elliptical galaxy or is an edge-on galaxy? So from the image, I would not know. From the light distribution, it's like dicey. You cannot be sure really. What we need is basically the motion of the stars, the kinematics, the dynamics. Then only we can be able to differentiate between. Okay, so we need to. Alright. So we know the light distribution in the galaxy, how they are in general. Okay. So what can we do here now? We can remember our aim is to do the dynamics. So from I of x and y, so let's say we know how to measure them, right? From here, this is the light distribution. So we can determine the surface mass density. This is the surface density of the light to be, right? So we can determine the surface density sigma of, let's say, R, just xy2 on the R, axis symmetric part. So this is the surface mass density. How do we calculate surface mass density? I measure this, right? How do you calculate this? I have light distribution, surface brightness. So you can also think about this as I of R. I just wrote this is I of R. Forget about the phi. Axis symmetry. So I have I of R and I want to estimate the surface mass density. How do you do that? You need to have a constant mass to light ratio. We need to have a mass to light ratio, some kind of constant, unless it is given to you, you won't be able to estimate this. Fine? Makes sense? So you need this mass to light ratio constant. Keep this in mind. From the surface brightness distribution, we need volume density distribution. This is a 2D, right? We need rho as a function of R. No? How do you get that? Any thinking? Do you understand the problem? What is the problem? What's the problem? Huh? This is surface mass density. This is volume density. The problem is very simple, isn't it? From here I need to go here. Can I go from, if I given row, can I go here? How? Suppose I am given row. Let's say to facilitate your thinking, I say row X, Y, and Z. From here I want to go sigma of X1, Y. What do we do? Huh? 1, 1. Multiply
with dv and dx,
dx, dy, dz. And integrate. What do I get? Mass. Mass. But I will need this. This is not the same, no? Is that same? Do you agree? I need volume density. I don't need total mass. What do you do? Huh?
sigma by dr.
Sigma by dr. Think about logically. Think about an object is oriented in the sky. It is a three-dimensional object. Like think about an ellipse or ellipsoid, right? You see projection in the sky, right? So that's what we measure here. But I'm giving a simple problem. So I know the volume density distribution as a function of z. How do I calculate the sigma? Go into dz. Very good. Go into dz. And integrate up to what is the limit? What this quantity will be after this? Sorry?
The mass density of the surface that we are looking for the integrate using that surface.
But I don't know anything here. What do you integrate? It's in space, right? Think we have a problem. That's like an ellipsoid, right? We don't even know how. You are right. So you will integrate from, you know the limit, right? But you don't know the limit, isn't it? What you measure here is measured. Because this is a measurable quantity. This is also measurable quantity apart from a constant. So it's basically it's a scalar quantity, no problem, right? Now, what we do here to here is non-trivial. It's not just a scalar multiplied by something which is like completely insane. But this is a non-trivial quantity. And we do not know what is the distance. So you integrate from minus infinity to plus infinity in general. To be safe, right? What is this quantity will be? What will you write on the left side? Which one? Can you be specific here? Sigma?
X1.
Huh? X1. So sigma xy is basically integration of rho x y z into dz, which means, think about this. When an object appears in the sky, you look through this, right, in the sky. So whatever comes along your line of sight, you integrate along that direction. So this is what basically it is. So as if this object is appearing in front of you, and the z direction is along your line of sight, where the projection happens, right? So this is an easy problem because you have a given volume density. You can calculate this, but I am given this. I need to calculate this. It's ulta, right? So this is not a projection. This is a deprojection. Deprojection problem. It's actually not so easy. You have infinite ways you can orient. You might get a similar solution. Okay? So it's like with computer graphics nowadays you can do much fancier thing. So you can like make simulation of like in such orientation in the sky and make a integration every time it matches with this, then okay, fine. You may also find that within a small changes will be able to match the density distribution. So many such orientations are possible. Okay, but one can limit this. RCAA is not possible, but there is an almost exact solution, or exact solution exists only when the object is a sphere. When it's sphere, whichever way you orient it will be same. Okay, so this problem. So this is a two problem from measurement of the surface brightness profile to surface mass density, you need the mass to light ratio, and from the surface density distribution to volume density distribution of the sun, you need the projection. Okay, both of these two are unknown. Both these are unknown. Okay, so let's say now we have drawn apart the volume density distribution. Okay, from there, what we can do now, we can go back.
So while considering the deep projection, to also consider the non-axial modeling.
Yes. Yes. That is actually complicated, but in principle, one should, because so this is actually should be done in that way, because this is what basically we measure. So from there, this is if you want to do, we should take into account the non-axis symmetric points. But we learn that that non-axis symmetric part of the density distribution versus the axis symmetric part. So if I want to take a ratio of this and one of this is within 10%. So okay, within that ground, but not mathematically correct. Okay? And exact to the exact nature is not correct, but you can ignore to a zeroth order approximation. And astronomy is very important. If you want to have a career in astronomy, you must appreciate and understand how to approximate. And also, this is a physicist's job. Okay, we often feel any problem and bring down to simple harmonic motion, isn't it? So it's always like that. So you must have an eye and also a brain how to bring down my problem, which I know how to solve, no matter how complicated it is. Okay, so that's where we go. So the zero, it's something called the zeroth order approximation, and then you build on it slowly. That is the way to do it. It's not unreal. So now from here we go back. We can calculate the potential for pi g rho. Okay, you can use many different ways to solve the equation, right? Is there anyone knows? Do you know? What's your name? Sorry? Muskan. Do you know how to solve this? Huh? Laplace. Can you tell me, is any solution that you know, which I can write here? No? Okay. Anyone else? What's your name? Arsu. Do you know how to solve this? No? Yeah. You have not studied in mathematical physics? Okay. Who knows how to solve? Separation of variables. You can solve this? Okay. Who said? Yeah, Green's function is of course one. There are many different ways. You can do there's a function method. You can do for example, this is a phi. You can write minus g rho of r prime d3 r prime divided by r minus r prime. This is a Green's function. You can now, the trouble is that the Green's function will be have a singularity at r equals r prime, So you cannot integrate this. So one can do an expansion of this. Okay, one can do many things into this. One can take R minus R prime. You can write this as a series expansion now. Okay, we can have monopole, dipole, quadrupole, down like that. So this is the multiple expansion method, right? You can also think about this as an elliptical integral method. Okay, okay. There are many ways, but I'm not going to. But provided that you know how to do this, of the many different. These are all textbook methods. Okay, so the phi can be calculated even a volume density distribution. Okay, so one can do this of the many different ways. One can think about this and calculate the potential. Okay. Okay. So we have come from all the way from observing galaxy, measuring the light distribution, understanding what the light distribution in general means, and from the light distributions we can go up to all the way up to volume density distribution if we know mass to light ratio and the projection, right? So once you know that, but we say that this is an exact method when the object is a sphere. So keeping that in mind, you can move ahead, and once you have the density distribution, we can calculate the potential. Fine? Yeah. All right. So for the time being, we will only talk the axis symmetric part of the galaxy. Only the axis symmetric part of the galaxy. So let's say we can calculate the potential of a galaxy, which is, let's say, x, y, and by the way, we talk a lot, we think about we can do this, but I think this is a task. Okay. Not difficult task because this integral is, as you can see, always done in an approximation. It's not obvious reasons. Density distribution may not be the correct one. Why? Because there are issues from the measuring the total light. There are uncertainty there. Mass to light ratio, which is an uncertainty there. So if I want to convert this to minus G, let's say light ratio times there will be a constant mass to light ratio, right? We have you can say the rho of R prime is the mass density distribution, and you can say the volume light density distribution is A of R prime. Okay, let's say A of R prime and V3 R prime by R minus. You can see already the potential is unknown by a factor, which is mass to light ratio. From the light distribution, we have actually measured, which is a 2D, like the surface brightness distribution. So there is this deep projection part comes into picture. Okay, so there is also a light, the unknown factor there. So the potential largely remains unknown for a galaxy. So it's a very difficult problem. Let's say for a hypothetical situation, we know the potential. Am I eating your tea time? When do I need to stop? It's time over? Should I stop? Okay, I'll take 10 more minutes. Okay, fine. So let's say so I hope you appreciate is that the potential is a very difficult to determine for a galaxy. But you cannot just make a statement, but I'm giving you the steps where is the difficulty comes from. Difficulty comes from measuring the exact light mass to light ratio and also the deep projection, which lets us not determine this. The deep projection is not only how is orientation we do not know, But for example, a seemingly simple spiral galaxy, which is a 2D, right? So you can think about on the species, this is like a phase-on galaxy, because how do you determine a phase-on? Because the B by A is very, from the B by A, which is the same major axis and the same minor axis ratio, you can say that okay, it's very small, so inclination must be close to 0. So it's a phase-on galaxy. Because, you know that this galaxy must be like a thick, right? It's like a cylindrical, like it's like a bowl, right? So it's like there is a thickness to it, right? Which is going backward inside behind, right? So which means that the stars are in a very like a thick, like a ball, this, and all is basically all the stars most likely rotate. Okay, it's like that thickness we do not know. Okay, so but when I say thickness in physically, it also means there can be a stratified distribution of stars, isn't it? So the density distribution that we talk about is rho. Rho can be as a R, rho naught of let's say in the plane, which is the R, and also let's say some function of let's say Z. If it is a, we talk about the axis symmetry, so now phi dependence part, right? So you can think about this. This is a R is a cylindrical coordinate radius, and Z is the height, right? And the phi is the azimuthal line. So the rho is independent of the phi. You can think about this as part is like volume density distribution somewhere, and there is a function of Z also. Okay, so that function of Z, in, for example, in a typical atmosphere, you know the distribution of the molecules on the surface of the Earth, right? This falls like an e to the power minus of height divided by some scale height, right? So there is a distribution. So anytime you have a self-gravitating object, okay, where there will be light distribution in the plane of the galaxy and also perpendicular to the plane of the galaxy. So there will be stratified distribution of light, which we do not see here. It's all integrated now. Integrated in a sense because when we talk about the rho, x, y, z, dz, the dz is a line of sight. So all integrated. You understand? So that's talking about. So fz has been integrated now. In a where we take a picture of this. Okay. So for example, just because we do not see any 3D image, we always see 2D, right? Because we are all integrated out in the along the line of sight. So there is this part also there. Okay. Now, so that is why it's a very very difficult problem to find out the potential of a galaxy. Okay. Nevertheless, as I said, that the people do try. For example, for E0, E1 type of elliptical galaxy and close to E4 elliptical galaxy, one can actually determine the potential of the galaxy. Okay, but for a spiral galaxy, it becomes a difficult problem because of this. One of the side is either when you look at edge on, you do not know along the arc. Because when you see edge on, you see only the vertical direction, right? If you see like edge on galaxy, this you see as this is along the vertical direction. On the plane, you see the thickness, but you don't see the arc, which is along you, right? So that's what is coming to us when we don't see it's all integrated. So then from this kind of galaxy we can find out what is the f of z, and from this distribution face on we can find out what is the r, and then we combine them and say that the all spiral galaxy must be to extent similar, and say okay, we can reconstruct by assuming that the same spiral galaxy, if we had looked into the edge-on direction, the vertical distribution will be different. So we can measure that, and one could actually find out, okay, this is the volume density distribution. So thinking this and putting in all this together, one can say that, okay, we know the volume density distribution, stars. Alright? And then we can say that to that extent only the potential is unknown. Okay? But we given this, you can find out the potential of the galaxy. Once you find out the potential of the galaxy, you can actually now write a Hamiltonian for the stars. Right? We can write a Hamiltonian for the stars in a cylindrical coordinate system. You know how to write an Hamiltonian? P square by twice m plus phi is a potential, given potential. What would be a cylindrical coordinate? Yeah. We have a P r, P phi, and P z. Fine? No? Do you know how? Or I'll not get into this, I'll go into other way. If you don't say how to write an equation here, how to write a P square here, I'll not get there. But I will take other routes. Anyone? I don't need to go there. I can just say that x double dot plus a minus gradient of phi. Newton's equation of what I want to do from there is that once I have a potential, I want to look at how the stars move in a galaxy. What kind of orbits they are. You have heard about orbits, right? The orbits of planets, similarly orbits of stars. What kind of orbits does, for example, our sun has? Sun goes around the galaxy center. Similarly, many stars goes around the galaxy center. How do this orbits look like? Right? I can go this way, or I can think about this way. I need to write the equation of motion. For example, suppose my potential, as I said, I have an axisymmetric distribution, means that I not in the Fourier transform. No phi. So no wiggly in the galaxy. It's all smooth. So then my potential cannot depend on phi coordinate. So it should be r and z. Agreed? Potential should depend on r and z. Do you think something will be conserved in this potential? Angular momentum, someone said. Says I can write an equation of motion of a star like this. Just x double dot is to minus square phi. So I have a 6 equation of motion. Right? 3 in the position, 3 in the position. First order. Right? You need to solve an equation of motion, just not so. If you have time, you can just go back to that, take a potential, then write a simple Python code, and you can just draw orbits. Okay, it's fun. But is there anyone who could go how to write this thing? This part you have seen, I believe. From there, I need to now PR, P5, PZ. Okay? Take your time, take your time. I just promised them, please. 2 minutes. Okay, so you need to go back to the find out. I'll talk about this tomorrow. So you need to do this equation of motion. So we write down the equation of motion first. Okay, either through this or through this is I have done already, so there is no first. But from this you learn many things. Because once you learn Hamiltonian of a system, you can actually there's a lot of benefits to it. So lots of quantities are come easy. So you do that. Okay. So then you go through this revision part and see if there is any question. So we can take it tomorrow. We can even ask right now. Tomorrow I plan to go into the dynamics part, which today I could start, but if we have learned these things, I will go.
So for the volume density function that we said that it's difficult to obtain because you can have multiple functions, which on integration gives us the same surface mass density. How do we know between, like, say, two guessed functions of volume, which one is right or wrong?
So you have so what you have is on the sky you have measurement of, let's say, I of x and y. Okay, so this is your measurement. Now you can take about some arbitrary I, and which is a volume density I of x and y and z, and then you say integrate along your line of sight along the projected axis, and you get some I prime, and then you go to match this. So you say maybe you can think about this as a chi-square also. So between I and I prime, there is difference if you are not correct one. So you have a delta I, which is like the difference, and you can minimize that difference by shooting different projected axes. That's how you do. So this is in computer graphics is done. Anything else?
PR would be del H by del.
Sorry?
Would PR be del H by del?
PR
Minus 10 x
Minus.
PR what? Dot or PR?
PR dot. Dot.
PR dot. Del H by del R. Sorry. Yes. And we find out del H by del pi equals to 0. So that gives you LZ conservation. PZ dot del H by del Z. So you need to solve this too, subject to the constraint, which is the angular momentum, which is a conserved quantity. Okay. It'll go ahead. But I will not go. But if you have any other question, please speak.
So how do we determine mass to light?
Mass to light ratio. This again, this of course is a difficult. Most of the things in astronomy becomes difficult. But how do you determine the mass to light ratio? So we have. So in a galaxy, for example, you have anyone talked about stellar population? Yes. Stellar population analysis. So you measure a set of stars and so that for the sun, mass to light ratio is a unit. So we basically measure a set of stars, their light distribution, and the stellar population analysis. From the stellar population analysis, we can compare actually from a standard how with respect to the sun how they are. So that's how we basically measure the mass to light ratio. But this comes from you need to do a. You cannot just say that okay, I have a star and then I want to do the mass to light ratio. It's not just that easier that way. But one has to, because from a galaxy you don't see any individual starlight, but it's a mix everything. So what you see is the integrated light. So from integrated light, one has to do some think about okay, there is a set of stellar population, there is a different stellar population which creates this light. Okay, and then compare with there's some modeling there. Yeah, I do not know. I don't think I can give you a clear answer just in one line, but maybe tomorrow